So now, how do we actually measure and control our acceleration during testing? The way we do that is with accelerometers. And the most common type of accelerometer, the one that we tend to use all the time, is piezoelectric accelerometers. And you can see I've put a figure here showing the basic makeup of how these accelerometers work. And essentially, it's just a mass and spring system, with the spring actually being a crystal. And as that crystal compresses or elongates, it's going to generate an electrical charge, which is then converted back to acceleration by your vibration controller. And the reason we like to use these piezoelectric accelerometers is because they've got very high resonant frequencies. And this is really helpful because it means you can use these accelerometers for a wide range of vibration tests. One of the main downsides to these is that they cannot measure very accurately at low frequencies. So pretty much anything below 5 hertz, they're not going to be very accurate. Luckily, most vibration tests are going to be above that level. If you do want to measure and test below 5 hertz, you can use a capacitive accelerometer. There are some downsides to those accelerometers though too. For instance, they're not great at the higher ranges. So like I said, we tend to stick with piezoelectric accelerometers, but you really have to choose your accelerometer based on the actual test that you're performing. Now, accelerometers are only as good as where you place them. So you really want to make sure that you're controlling your acceleration as close as possible to your input vibration location. So you want to place it on the fixture itself, not directly on the table, and you want to have it near a mounting location and on a rigid member. One exception of this is, for instance, if you're performing transportation testing. For these tests, a lot of times there actually is no fixture. You're just placing the DUT directly on the table and letting it move about freely during testing. So in this case scenario, you actually would place your accelerometer directly on the table itself for control. Now, speaking of accelerometers and controlling vibration with them, there's a few different control strategies that can be used. Essentially, you can either control with one accelerometer or with multiple accelerometers. Most common control strategy is just single control. That's what we use a lot of times, and that's just using one accelerometer. But you can also use multiple, and there's a few different ways to do that. You can use maximum or minimum control, and the way that works is maximum controls based on the accelerometer that's experiencing the highest level of acceleration. And a minimum control does the exact opposite of that. And the reason you might want to do that is, for instance, let's say you want to make sure that no point of your DUT experiences a level above, say, 5 Gs if you're performing a 5G test. What you could do is you could place multiple accelerometers around your DUT. You could use a maximum control strategy, and that way you could ensure that no part of your DUT is going to go over that limit that you've set. The only downside to this is you're going to have some undertest. Certain parts of your DUT are going to experience undertest, and if you're using minimum control strategy, you're going to have the opposite issue. You're going to have some points of your DUT that are going to experience some overtest. Another option, if you're going to use multiple accelerometers, is to use an averaging control strategy. That takes a weighted average of multiple accelerometers. This can be useful because it does help to minimize the effects of spikes in acceleration, but it's important to keep in mind that an averaging method cannot correct for improper fixturing.